It's my pleasure to introduce Ethan Range, who works with Jeremy Yallop on safe pattern generation for multi-stage programming.
Hi, everyone. My name is Ethan Range, and I'm going to be presenting some work that I did as part of my master's dissertation at the University of Cambridge, supervised by Jeremy, on generating pattern matching expressions in multi-stage programming. And so, for the benefit of anyone unfamiliar, I'll start with a little bit on what multi-stage programming actually is. So, multi-stage programming is a variety of metaprogramming. What is metaprogramming? Well, metaprogramming is ways of generating code in which we can have representations or fragments of the code as data within our language and separate that compilation out into multiple stages. In this work, we use the style of multi-stage programming found in the ML24 language. In particular, we can take some expression of a type A and take a quotation of that to get a code fragment of type A code. And we can also splice one of these code fragments back into the program. So if we have a code fragment of type A code, we can splice it back in to get the underlying A expression. And ML24 also provides the ability for us to run these code fragments with the run operation, which simply takes a code fragment and executes it. One of the things which is quite useful for multi-stage programming is optimizations and generating optimized code. And so we'll turn to look at a type of optimization called list map unrolling. And we can define the higher order map function over lists as in the classical way. So mapping a function onto an empty list gives us an empty list. And in the recursive case, we apply the function to the head of the list and cons that onto the recursive call on the tail of the list. But what we can actually do in order to get a performance improvement is we can take this map function and we can actually unroll this recursion. So instead of processing a single cons cell at a time, we can instead process multiple cons cells at a time and append them to the front. And what we also have to do is we need to add a catch-all case at the end for applying the map to any lists which have a length shorter than the depth of the unrolling. And what's interesting about this unrolling is we can actually do this to an arbitrary depth. So here we've unrolled it one level, but we can actually unroll it as many times as we'd like. The interesting part of this is that depending on precisely how we're using this map function, the data which it operates on, and potentially even the hardware of the system which we're running on, the optimal depth for this unrolling is going to vary. And so it might be quite a nice idea to use staging as a way to generate different versions of this map function on the fly to ensure that we're using the one with optimal performance. So we can have a look into some ways of doing this. Well, one approach we might look at is using an untyped multi-stage programming system. So an example of this would be the untyped template Haskell. And this is very nice. It provides us the tools we need to be able to build up these arbitrary patterns. The problem we run into is that suddenly we've thrown away all of the guarantees we have about the well-typedness and the well-scopeness of the code we generate. And this isn't ideal. So we might look into a type metaprogramming system, such as ML24. And ML24 does indeed provide ways of generating patterns. As we can see here, it actually is quite clever and it exploits the OCaml syntax to define cases of a pattern matching expression as a code fragment, which is a function. And here we define both the pattern and the body as part of the function. And this is nice. This allows us to define a certain class of patterns. But if we want to try and apply this to our case of generating list maps, we run into an issue in that every single pattern which we use in a case must be statically known up front and defined. There is no way to kind of build these on the fly based on some dynamic value. And so what we're really looking for is a more powerful way to build up patterns and pattern matching expressions in metaprogramming. And that's precisely what we set out to do with this work. So we want to build up, we have a system which we can, in a type-safe way, build up arbitrary patterns. And we want to do this by having a much more modular approach to building up patterns and bodies. And I'll touch on exactly what I mean by that later. So in order to do this, we have 4 main steps. So first, we're going to need some way to actually define these patterns. So ML24 provides their very atomic way in which we can state up front, but we want a much more flexible modular way of doing this. Once we've actually specified our patterns, we're going to need some way to describe the bodies. So MetaOCaml does it with a fragment of code, except we're also going to want the ability to bind variables within a pattern and include these within the body. Once we've got both a pattern and a body, we then need to look into generating cases and generating code from these cases, all at the same time ensuring that the code remains well typed and implementing the appropriate checks. And finally, once we've achieved this kind of parity with MetaOCaml, we need to look into the idea of generating these statically unknown patterns, which we'll need for the map functions. So we'll first look into the idea of describing patterns. So as I said, MetaOCaml does provide a safe way to define patterns, but it lacks the modularity. And here's precisely what I mean by this, in that we may have patterns such as this with an xcons and x's, and also a tuple of x1 and x2. And it's quite conceivable that we might want to build a pattern from these in which we can substitute the x1, x2 tuple for the x. Unfortunately, that's not actually possible with the way MetaOCaml is implemented. And so what we introduce is the idea of a domain-specific language to specify these patterns in which the terms can be used to build up an arbitrary pattern. And so, as I show here, there's a subset of our DSL in which we can define many of the common patterns which are found built into OCaml. So, for example, we can define wildcard patterns, integer constant patterns. We can find variable identifier patterns. And we notice actually that instead of actually explicitly having to name the patterns as you would in OCaml, we can instead describe a pattern as a variable and don't actually need to have an explicit name and allow that to be generated instead. We have empty list patterns, more constant patterns, and then these compound patterns, which allow us to combine two existing patterns to produce a new one. So on the left is, of the two is the tuple pattern. So if we have two given patterns, we can match on a tuple of those two. And on the right is a list cons pattern to do very much the same. And it's quite important to type these patterns to ensure that we only generate valid code at the end. So there's a few reasons why we will do this specifically. Perhaps the most obvious is that some patterns are completely invalid to be even thought of. So it's very reasonable to think of consing an integer onto the tail of a list represented by a variable. But actually, it makes no sense to cons something onto an integer constant. And so we need to make sure we can reject patterns like that on the right. But then there are other issues. So we need to make sure that the patterns we define are compatible with the bodies which we pair them with, and also make sure that all the cases within a pattern matching expression are compatible in both their input and return type. And we'll revisit that idea later. So in order to do this, we introduced the idea of a pattern type. And this has 3 type parameters in it. So the first, the A, is perhaps the most simple, and it's simply the input type of a pattern. So if we have a pattern which matches on an integer constant, that can't be compared against with a string, for example. Then for the next 2 patterns, which we'll explore in a bit more detail, the F pattern is what we call the pattern body context type, which is effectively a type which represents what types of bodies this pattern can be paired with. And finally, the R type is the return type of the body of a pattern matching expression. Now, it seems counterintuitive that why would the pattern need to reflect what the return type of the body is, but we'll come back to that later and see that it is in fact necessary to have that there. So now we've got a way of specifying patterns. We can look into the problem of specifying or defining pattern bodies. So given that the body is just a code fragment, it may seem as the most natural approach to simply define the body as a code fragment. However, what we want to retrieve from MetaOCaml's implementation is this ability to introduce bindings in the pattern and have them present in the code fragment which represents the body. And so in order to do this, we have the idea of representing the pattern body as a function. So this function takes the form as shown, and we effectively use the parameters of the function to represent code fragments, which are the variables bound within a pattern. And then the return type is the body of the expression which represents the body. And so a couple of examples of this, if we have an integer constant 2 pattern here, we see that actually we bind no variables, and so the function has no arguments, and we can return a code fragment of just a Boolean, for example. Whereas if we have a tuple of variables pattern, we see we have the x and y, which correspond to the 2 variables being bound, and we can show that we can use these pattern variables to actually do something in our body, here, adding them together. So if we look at this pair of variables again, we can see that if it's combined with the addition body, we can see that the input type is going to be constrained to be a tuple of integers. The integers because they must be added, and the tuple from the shape of the pattern. If we look at the shape of the body, we see that we have 2 code fragments of integers representing x and y respectively as the parameters into the function, and then we return a result type, which is the fragment of an integer. And again, you'll see that the R type is in fact just a duplicate of the return type of this f function. But again, we'll see very shortly why that's necessary. So if we look more generally at our DSL terms, we can start typing some of them. So for an integer constant pattern, if we provide it an integer on which it should match, we constrain the input type to be an integer. We can't pass a string to an integer constant pattern. But we actually impose no restrictions on what we do with it in the body or the return type of the body. If we consider a variable pattern, actually we don't constrain the input at all. Our variable identifier can match onto any type of value. But what we do is we introduce a new binding. So this variable gets bound and is available in the body. And we don't actually constrain the return type in any way. And now on to why we do actually need this R type in the pattern. Is the idea of the compound patterns. So this is the tuple pattern I mentioned earlier. And we use a approach based on difference types in which effectively we take the combined pattern, the tuple A and B, and the input type is simply a tuple of the input type of the first and the second pattern. But for the function type of the combined pattern, if we apply if we provide values for all the bindings in the first pattern to this combined pattern's body, we need to end up with precisely the function which encodes the body of the second pattern. And that's the reason for shaping that. And there's much more on that in both the paper and my dissertation. So now we actually have both patterns and pattern bodies generated. We move to the idea of generating cases and generating code from these to do something with them. So if we have both a pattern and a body, we introduce this idea of the arrow operation. And this just says to us, if we have some pattern which is expecting a body of type F, and we provide it a suitable body of that type F, then we can produce a case of this. And that's just a case in a pattern matching expression. Now, the A and the R type parameters in this case are doing exactly the same as the A and the R type parameters in the pattern type, namely the input and output type. And you'll notice that the F type has been dropped. And this corresponds to the idea that the variables are bound within the pattern. And once we're outside of the pattern body, we no longer need them, and they're dropped. And we can use this exactly how you'd expect. So if we take our familiar pair of variables example and combine it with the addition example, this gives us a case which expects us to pass a tuple of integers, and we return an integer. Now that we've actually generated some cases, we can make some code using them. So here we have a match code generator, in which if we provide some code fragment of a scrutiny against which we compare the patterns to, or we compare against the patterns, and a list of the cases, we can then generate some result type based on performing that match. And this is used precisely as you'd expect. So if we provide it a particular scrutiny, here the tuple of 1 and 2, and our pattern which we've built up, we generate precisely the code you'd expect with matching the scrutiny on the values and producing the sum of them. Now, there's a few things to note in this. One is that the match combinator actually ensures the compatibility of the cases. So we require all the cases in the list to share both the input type and the return type. There's a few other things we need to take care of in this process, namely that we need to uniquely generate the names of the variables bound within the pattern. uniquely generate the pattern variable names to ensure that we don't accidentally capture any scope, accidentally capture any variables from a higher scope. And we also need to take care in scope extrusion. So now we've introduced these bindings of R0 and R1. We need to ensure that they can't escape, possibly through some mutability like a reference. And for both of these second issues, we take the meta-OCaml's approach, particularly the dynamic approach of detecting scope extrusion. Take a break for water. So at this point, we've very much achieved parity with meta-OCaml in that we can build any patterns which we can statically define in advance. So what we want to do now is try and extend this to building the statically unknown patterns which we'd like. So in order to do this, we have two stages of this. We need to both build up the pattern itself arbitrarily, and we also need to build up the body on the fly. And we run into issues with both of these. So in the first case, it seems relatively simple that using our DSL, we might be able to build this up recursively. And in fact, we do run into an issue with this, which is namely the F-type in the pattern. So depending on the number of variables being bound in this list cons pattern family, we see that the F-type varies depending on a dynamic value. And so in order to actually be able to define this with recursion, we need to find some way to prevent this F-type from being leaked out. We also have the issue with generating pattern bodies in that we need some way in which we can generate expressions which potentially can handle an arbitrary amount of variables bound within a pattern. So we'll solve these issues in reverse order. So in order to generate pattern bodies, we introduce the idea of an inductive code definition. Now, an inductive code definition very much follows the structure of a classical inductive definition, so with a base case and a recursive case. So here, our base case for the list cons example, we provided the tail of the list, and what we want to generate from this is some code fragment as a return type. And for the inductive case, we pass in both the v, which is a newly bound variable within the pattern, and the accumulated body, which has been built up through this inductive definition. And on the right-hand side, we can define precisely how we incorporate this newly bound variable from the pattern into the overall body. And by repeatedly applying this, this inductive definition, we can build up a code fragment which uses arbitrarily many patterns. So here, for example, we're defining a sum of arbitrarily many values. Now, in order to solve the issue of exposing the F-type in patterns, we can use existential wrappers. Now, this is not as immediately simple as it seems, in that we run into a few issues with trying to define this, particularly around the opaqueness of the existential type. So because the existential type is completely opaque, it forces us to build up both our pattern and the body simultaneously to ensure that when we try and combine them with that arrow operator, they can in fact match, so as the existential types, although completely opaque, are the same. We also run into the issue of if we're trying to wrap and unwrap the body definition and imply inductive definitions, because of the opaqueness, we're not actually able to apply them. And so instead we need to use a continuation-based approach in which the effects of the inductive definition are encoded as continuations from our code to our code. And then we queue them up, compose them together, and then apply them a single time, which avoids the need to wrap and unwrap some value, which gets opaque. And so we end up with a wrapper of this type. So as you see, the F-type is no longer present on the outside, so we're shielding it as required. In this specific case for the list map example, we can restrict the pattern to be a list pattern of some number of conses. And you'll see the other thing we pass in is this idea of a continuation, which will produce our F, which is the body. From this definition of a wrapper, we can then define some combinators to generate statically unknown patterns. So in this example, we'll generate a n-cons pattern, so n variables cons together. And this can be done by passing in just a numerical value, a dynamic value, as in the number of cons cells to be built up. We pass in the base and inductive definitions, so we can generate the body we desire. And from the end of this, we'll get some case in a pattern matching expression, which accepts a list and gives us some result. Now, I won't go into full detail on this, but here is where our wrapper comes in. So we have some internal loop, which builds up both the pattern on the left by consing a var onto the existing pattern, but also building up the body on the right using the composition. And this is all wrapped so that the recursive call on the loop, the type remains the same, and we can actually define this. And once we're done with constructing this, we can simply extract out our pattern by pattern matching on the wrapper, pulling out the pattern and the continuation, retrieving the body by applying the continuation to an identity, and then constructing them with the arrow operation. So does this actually work in practice? Well, it does. So we can now define the list unrolling, which we set out to in the first place. So we can define a function, which is to generate an unrolled map for some arbitrary n integer. And we can set it up to generate a function and provide it a list of cases. And very much in following the structure of the original example, for the case of an empty list, we can provide an empty list. We can use our gen-n-cons combinator to build up the case for an arbitrary number of con cells. And here we see that in the base case, we simply fall back to the recursive call of the function we're generating. And in the inductive case, we're processing yet another con cell and tacking it onto the front of the body. And finally, we need to define the catch-all case for any lists shorter than the unrolling depth. And this does, in fact, work. So if we compare this map, a selection of different implementations of map functions in the green on the left versus a variety of unrollings, we see that not only does unrolling actually make it faster, which is useful for the motivation, but we also see that comparing both handwritten and generated versions of our functions, we see that the performance is roughly identical, and we can use something like this to determine that an unrolling depth of approximately 16 would be optimal in this case. So where does this leave us now? Well, what we have now is we have a type-safe way of generating arbitrary patterns, so both static and dynamic, and a broad class of bodies with this idea of an inductive code definition. And we also have a very extensible core system, so we can extend it both in terms of alternative pattern types, but also it's a very portable system, so it's applicable not just to MetroCaml, but also to other multi-stage programming systems, be they within the ML family, such as MacoCaml, or even outside, such as Template Haskell. There is still plenty more that we're looking at, though. So in terms of implementing this into MetroCaml, the original work was built as a library on top of MetroCaml, and that leaves some caveats with detecting scope extrusion. So that's a work in progress to fix at the moment. But in the longer-term future, we're also looking at implementing some alternative pattern types. So while it's perhaps there are some very simple examples, so extending with string constant patterns would be very simple. There are a number of interesting problems to think about with alternative patterns, things such as GADT patterns, polymorphic variant patterns, and even things such as disjunctive patterns if we bind the variables in different orders within the disjuncts. And other things we're looking at are areas which we can apply this to, and this idea of building up patterns on the fly beyond just unrolling optimizations. So things such as potentially generating patterns on the fly for searching or querying. If you're interested in this and fancy reading more, I've got a whole host of links for you to look at. So the source code for this original implementation can be found at the first link on my GitHub. You can read the extended abstract, which is a 2-page format. Or as I said, this was done as part of my master's dissertation. So if you want the full detail with quite a lot of commentary on different approaches and design choices and the kind of history of the techniques, you can find that there on my website. And there's also the work in progress implementation into MetroCaml, which I mentioned a few slides ago. Thank you very much for listening, and I'll be happy to take any questions.
Thank you for the fun talk. I wanted to ask about, at the end you mentioned thoughts about supporting more complex patterns in the future. And I was curious particularly about patterns, for example, involving record labels. And if you thought at all, not just about how to have patterns with record labels, or I guess the same thing applies to variant constructors, but how to abstract over the exact name of the label, if you know what I mean.
Yeah, so it's not something which I've looked into too much so far. It was very much, development's focused on the kind of core system without trying to get too creative with it. But yes, I think there is, record types are certainly something which we definitely look into. And I think the next step would probably be just data structure definitions in general and ADTs with custom names.
Thanks.
Hi, thanks for the talk. On your benchmarks, you showed there was a small gap between the generated definition and the handwritten definition. I guess what tricks remain in the handwritten definition that weren't generated?
So actually, the approach taken, the types, changed quite a lot from where we started in this. And the main reason for those changes was the generated code is designed to be as close to how you would handwrite it as possible. And that's actually what we've achieved. So the differences you see there are actually just random benchmarking differences. The code generated is nearly identical with one slight caveat, which I'm happy to talk about if you want. And while that made some parts of it more complex, it certainly aids in the readability of debugging these kind of things.
Okay, thank you.
Sorry, I missed the very end of your talk, so maybe this was answered, but wouldn't it be simpler to, instead of generating a curried function with all the pattern variables in a flat form, why not generate a nested structure, like nested tuples, so that it reflects the actual pattern shape, and you don't have to do this existential stuff, maybe?
Yeah. So, yeah, I think this one was quite nice in that there was both the simplicity of a flat structure, and also there was there's some existing work on kind of first-class pattern representations as functions. There were a lot of contrasting ways, and actually, Jeremy and I had some interesting conversations with Matthew Pickering and he had a few different approaches, yes, both in type-level ways of doing it and also tupled approaches. So there's lots of different ways. They each have their benefits. I haven't tried enough of them in any depth to comment of which ones are better and why.
I see. Yeah, it sounds like it would be a little bit simpler because you wouldn't need the intermediate type. You could just have two type arguments. And you wouldn't need this existential stuff, right? You don't need to flatten anything. You don't need to do some sort of type level computation because the pattern type just reflect its structure.
Yes,
okay.
I'd have to have a look at it.
Yeah, yeah. Okay, thanks.
So I have one additional question. Have you found during this work any use of it that you did not expect at the start? So
actually, that's one of the things I mentioned in the looking for more applications is that I very much got to the end of this. I never set out to do this in the first place. I set out to play with staging for optimizing data structures, and instead went, I can't do this. I wonder how difficult it is to solve this. It turns out it took a little while. And so I haven't looked too much beyond where else this can be applied. Actually, just a few days ago, I was thinking of this idea of being able to generate patterns on the fly is quite interesting for possibly things like searching or querying on the fly. But also, there's ideas around generating more interesting patterns. So patterns which we can't express in, say, OCaml natively, things like view patterns, or even things like can we union two patterns together or intersect two patterns together. This kind of work can be extended in that direction to allow us to do things which we never could with the base language.
Thank you.